Welcome back. In this lecture, we will cover the basis on which we make approximations in fluid mechanics. The equations governing the flow of fluids form a system of simultaneous second-order nonlinear partial differential equations which are formidably complex. Closed-form analytical solutions to these have been obtained for some very simple geometries and for very restrictive conditions. In such cases, one or more of the terms from the flow equations drop out because of some or the other simplifying features. But such features are not encountered in general. The solutions obtained through these simplifications are so cherished that we like to extend them to the realistic situation where these conditions are not met exactly. And so we have to resort to approximations. If we were predicting the global weather using thousands of equations on a supercomputer and someone suggested that we are making a mistake by not including the effect of the flapping of the wings of a distant butterfly several weeks earlier, we would simply have laughed it off. But consider that in December 2019, a gentleman in the city of Wuhan took some bat soup, and soon there were repercussions which were beyond imagination. The whole world got infected with COVID-19 virus. Up till now, 90 million people have been infected, 2 million have died. The medical facilities are under severe stress. The cities have been locked out. The schools and colleges shut down, and the economy is shattered. Could this butterfly flapping its wing result in a tornado? A few months later, Edward Lorenz in 1961 found that a very simple rounding off of initial conditions while predicting the weather through a numerical model resulted in a massive deviation in prediction of weather about 2 months down. He named it the butterfly effect, and it led to the development of the theory of deterministic chaos. In this graph that we are showing, we started out with 3 solutions with boundary conditions slightly different, only slightly different. After a while, the 3 solutions diverged. But still, the practice of engineering proceeds on the principle that small causes produce small effects. So if we can show that a cause is small, the expected results are small, and so we can neglect that small causes. And we shall persist with this principle till something goes wrong and we'll have to reconsider. So we need to determine which terms in the governing equations are negligible, and for this we need to estimate the magnitude of various terms, and so that we can neglect terms which are small in magnitude compared to terms which are larger in magnitude. One very powerful method of making such estimate is to normalize each variable by scaling it with its characteristic value. If the characterizing values of the quantities are chosen properly, the normalized variables are then expected to be of order unity. That is, except at certain isolated points in the flow field, the values of the transformed variables are expected to be neither very large nor very small compared to unity. Further, it is hoped that not only the variables but the dimensionless derivatives of the various physical quantities appearing in the equations are also of order unity. Let us consider the flow past a circular cylinder of diameter d, a fluid at a faraway pressure P naught and a faraway velocity which is pulsating like V naught sine t over tau flows past the cylinder. Following the procedure discussed earlier, we can normalize the various variables. X star is equal to x by d, z star is equal to z by d, t star is equal to t by characteristic time, and the time period of pulsation tau could be a characteristic time. U star, the velocity in the x direction, is u divided by v naught, the magnitude of the, or rather the amplitude of the free stream velocity, and W star is equal to W divided by V naught. We could non-dimensionalize pressures as P star is equal to P by P naught, the standard procedure. And if we do this, this is the form of the resulting continuity equation and the Navier-Stokes equation. Unsteady flow, and as before, we see that the various parameters are now concentrated as non-dimensional coefficients of the various terms, and the boundary conditions are non-dimensionalized into these. The coefficients of the various terms, which are nothing but non-dimensional groups of various parameters, form the pi numbers as we have discussed a few classes ago. The various pi numbers like Strouhal number, Reynolds number, Froude number, Euler number, Weber number, Cauchy number, Strouhal number again for centrifugal forces. So that this equation, the first term is the unsteady term, the second is the convective acceleration, and we have rendered the coefficient of this as unity. The first term on the right is the pressure term, the second the gravity, and the third the viscous term. Since the coefficient of the convective acceleration term is 1, the coefficients of the various other terms measure the relative magnitude of those quantities with respect to the convective acceleration. We recognize d by v naught tau as the Strouhal number, and this we clearly see as the ratio of unsteady forces to the total forces, the inertial forces, the convective inertial forces. The second coefficient P naught by rho V naught square is recognized as 1 over Euler number, and P naught by rho V naught square would then be the ratio of the pressure forces and the inertial forces. The third term is recognized as 1 over Froude number squared, because Froude number is V naught divided by under root G d. And this is the ratio of gravity over the inertial forces. The coefficient of the last term is 1 over Reynolds number, and which is viscous over inertial forces. the ratio of the typical viscous over inertial forces. So clearly magnitudes of these coefficients tells us something about the importance of these terms in this equation. If any of these coefficient is much less than 1, then the term is negligible compared to the convective acceleration term. Let's do an example of carrying out this analysis, and this is concerned with spreading of oil slick when there's oil spill in oceans. The spreading of oil slick on seawater is controlled primarily by the viscous forces that the seawater applies on the slick, the unsteady inertial forces, and the buoyant weight of the slick. That is, the weight of the slick minus the buoyancy force. The surface tension forces are unimportant in the initial period of the oil spill and come into play much later. Can we estimate the time that it takes for the surface tension forces to come into play? Clearly, the approach would be we would estimate the surface tension forces and see if it contains any time parameter. Then as long as the coefficient of the surface tension force in the non-dimensional equation, that is an estimate of surface tension force with respect to the inertial forces, is much less than 1, then the surface tension forces are negligible. But they would come into play when that coefficient approaches the value 1. So we estimate these forces. The surface tension forces are estimated as, or sigma times LC, where LC is a characteristic length and sigma is the surface tension between the spilled oil and the sea water. This is the force which tends to stretch the slick wider. The unsteady inertial forces in the slick which oppose that stretching are estimated as before. Inertial forces characteristic would be the characteristic mass multiplied by characteristic acceleration dv by dt, and the mass is estimated as the rho of the slick times the characteristic length cube, that is like the volume, multiplied by the unsteady acceleration, which would be like Vc by Tc. And so this is an estimate of the inertial forces. So surface tension forces are negligible as long as this over this is small compared to 1, which is here. This contains Tc, and as the time increases, this parameter increases. Let's estimate for what time would this become of order 1. That is the ratio that we obtained. The characteristic length Lc can be taken as the cube root of the volume of the oil that is spilled. The velocity Vc can be estimated as Lc by Tc. The actual time t can be used for the characteristic time, and the relevant criteria then is that this is negligible as long as t is less than under root rho of the slake times the volume of the oil divided by the surface tension between the oil and the seawater. So the surface tension does not come into play for T less than under root rho s V divided by sigma. For typical values of rho s and V, this may yield a period of several days during which surface tension force is not significant. One estimate of seawater crude surface tension is 0.02 Newton per meter. 100,000 tons oil spill, which is considered a medium size spill. The above equation suggests that the surface tension forces do not show up for times of the order of 20 hours. So for the initial 20 hours, the surface tension forces can be neglected. And it's only after that the surface tension spreads the oil on water. This picture shows a 15-year-old slake in the Gulf of Mexico. The colors are visible for the film thickness between 150 nanometers and 1 micrometers. So the oil has thinned out into a film so thin. Let us illustrate these concepts further by taking a problem in which a fluid is confined between two plates. The upper plate is stationary, but the lower plate is oscillating at a velocity of V naught sine omega t. The gap between the plate is B. Let's estimate the forces. The unsteady forces, which are like mass times acceleration, would, using our usual procedure, result in an estimate of this, where the subscript C denotes that these are the characteristic quantities. The viscous forces are estimated as mu times the area times the velocity gradient, and as before, it comes out to be mu times LC times VC. The natural or the characteristic values of the various quantities are LC can be taken equal to B, VC can be taken is equal to V naught, the amplitude of the velocity fluctuation, and the characteristic time can be taken as 1 over angular velocity. If we do this, the ratio of the unsteady forces to the viscous forces is estimated as rho b square omega by mu. The ratio rho b square omega by mu then determines the relative importance of the two types of forces. If this value is small, that is, if omega is less than mu divided by rho b square, the unsteady effects are small and may be neglected in comparison with the viscous forces. Once the unsteady effects are neglected, the governing equation would require that the net viscous forces be 0 on this element, because the governing equations is a balance of unsteady forces plus the initial forces equal to the pressure forces times the viscous forces. Because of the geometry, the pressure forces are 0. Because the flow does not change in the x direction, the inertial forces are 0. So the governing equation just balances the unsteady forces with the viscous forces. And if the unsteady forces are 0, That means we can neglect the left hand side. Then the only term remaining in the equation would be the viscous term is equal to 0. The net viscous force should be 0. Del square Vx by del y square is 0. This is the solution that we obtained for the Kuwait flow. There is no net viscous force. This equation is to be solved with Vx is equal to V naught sine omega t at the lower plate and 0 at the upper plate. For omega less than mu divided by rho b square, which is also nu divided by b square, where nu is the kinematic viscosity. The solution looks like this. The solution is a straight line, but the boundary condition at the plate changes with time. V naught sine omega t. That's why it's a straight line profile which is swinging between two extremes, minus V naught to plus V naught. At any instant, it is a straight line. This is a quasi-steady state solution. At any given moment, we can neglect the inertial forces within the fluid. We can treat the fluid to be steady at any moment and solve for the instantaneous boundary conditions. But those instantaneous boundary conditions are changing with time. They are changing slowly enough for this setup so that at any instant the profile is as if it is a steady flow with the instantaneous velocity of the lower plate as the velocity of the lower plate and 0 as the velocity of the upper plate. A very interesting solution. This is all for omega less than nu divided by b square. The rate of change of velocity is slow compared to nu divided by b square. B square by nu, the reciprocal of that, can be named as the penetration time tau. This is the time it takes for the effect of the motion of the lower plate or change in velocity of the lower plate to penetrate up till the upper plate. More the viscosity, lesser is the penetration time. In a very viscous flow, the penetration is almost instantaneous. Now, if omega is much less than 1 over this penetration time, then at any instant, the effect of the change of velocity of the lower plate penetrates almost instantaneously to the upper plate. And that's why we get a quasi-steady flow. If the time period 1 over omega of the oscillation of the lower plate is much more than the characteristic time, the motion of the plate is so slow that the unsteady inertia of the fluid can be neglected. This is what we showed in our discussion. Alternately, we can consider nu divided by omega. From this, we get b square is equal to nu divided by omega, or b is equal to under root nu by omega. We can consider under root nu by omega as the penetration depth LP, P for penetration. defined as the distance through which the viscous effects penetrate in time 1 over omega. 1 over omega is the time period of the fluctuation, or related to the time period of fluctuation, which characterize the motion of the lower plate. Therefore, for B much less under root nu by omega, or the gap between the plate less than the penetration depth, we can imagine that the effect of the motion of the plate penetrate throughout the thickness of the fluid layer before the motion of the lower plate changes direction, or that the oscillation appears too slow to the fluid and it can be assumed to respond instantaneously. Same thing we said in the last slide, repeated in different words.